looking for positive integer solutions to this strange looking fractional equation. Again, positive integers, natural numbers. Okay, so we have a summation of a bunch of ones and the product of a bunch of twos. So we have a constant summand and a constant factor here. But here's the problem. We have this strange looking decimal that would be better if we wrote this in a fractional form. So that's probably the hardest part of the problem. So here we go. 0.90625, and I just successively divided fives. This is mental math. It's not particularly difficult. I divided by 5 repeatedly. Got to this stage, folks, and you'll notice also that dividing by 5 will lead to 29 over 32. Okay, so again, that took some time there, but it's doable without a calculator. Okay, now, so what are we going to do? Well, we're going to set our original problem equal to that. So this is equal to 29 over 32. Now, this is a reduced fraction. 29 and 32 are co-prime, relatively prime. And so we can actually set 29 equal to the numerator and 32 equal to the denominator. Okay. Now, it's a little easier. Probably, actually, we need to do the denominator first. So notice right here, if we set, let's see here, pi, which is product notation, folks. I'll take the time to write the index underneath. This Microsoft Word equation editor does strange things, but this looks a little more readable to me. I don't know about you guys. All right, of 2 equals 32, right? It's okay to do again. This is a reduced fraction, so we don't have any problems here. Now notice that this has to equal to, we need 32 is equal to 2 to the 5th, right? So we need this upper limit to provide that number of multiplications. But notice that's going to happen when n is equal to 11. It's a little confusing, but if you just think about this, it's like a lot of this stuff is factorial stuff. It's always going to be one more than you think. For example, if n were 8, okay, you would go, I would be 1, I would be 7, I would be 8, and so it would be 2 times 2, right? So you have to actually subtract and then add 1, okay? So n equals 11 is the solution to this. And again, not too hard to verify, folks. Just think of just think of 11 being here, right? Where you would go from 7, just count 7, 8, 9, 10, 11. That's 5 times that 2 is being multiplied, right? And we get the 2 to the 5th right here, okay? So we actually know that n is equal to 11. Now let's see what we can do using that with the top part. The top part, the summation, I equals n. And that is the constant value 1 in there, folks, as the sum in of k. Okay, of just 1, we're adding up ones, right? We're making ones conspicuous there like a Roman 1. Okay, that equals to 29. Now, in a very similar fashion, we already know that n is equal to 11, right? From this work over here, we know that n is equal to 11. And in the same kind of fashion, we can see that k must be 39. This implies that k has to be 39. And again, it's exactly the same kind of reasoning. Think about this. 39 minus 11 is 28, but you add 1 to that to get 29. Again, if you think of k equals 39 right here, you might just think, oh, 39 minus 11. It's a common mistake, but there's always going to be one more summand or one more factor as we saw over here. So those are the two solutions, folks. K equals 39 and n equals 11 are the solutions, both positive integers. Thanks for viewing.